fellow Haskellers! This time will be very different from last time. So, in the last stream, I live coded some Haskell, a very simple program that animated the counter you just saw in the waiting time. And this time it will be different in two different ways. First of all, we'll be doing Agda instead of Haskell. And second of all, I won't be coding it live because it took me like several weeks to write it the first time. So it would have been a very long stream if I was coding it live. And I want to give you first a little bit of background as to what is this program that I will be explaining to you. So it's a program that I wrote in response to a challenge. One good way to get me to write some code is to give a challenge on Twitter, and then I find it and I decide to implement it. There was a previous challenge. I made a video about that. I should probably link to it if I can find the link. Better yet, I should find it here on the stream. So on haskellcat.com, that's my link to my YouTube channel, which has all of the recordings of my streams. And before I started doing streaming, I did another Agda Cat, this thing here. I won't play it for you, but I will paste it in the chat, and if I remember, include it in the YouTube description once I post the stream to YouTube. So anyway, the idea is, well, the idea was the first time there was a challenge that had been challenge had been posed on Twitter, and I thought it was an interesting challenge, and so I did it in Agda and explained all of the steps. This time is similar. Somebody, Payan or Kat Nahwek, they asked as a challenge to explain, they asked to explain it to Rust or Haskell, but like the general gist of it was, how can you explain very complex things about an algorithm, complex guarantees, to a language that has a fancy type system such as Rust or Haskell. And so I used a language that has an even fancier type system. I used Agda because I wasn't like 100% sure whether it was possible to encode that particular constraint in Haskell. Might be an interesting exercise to do that next. But for now, what I have is an Agda implementation. And okay, so an Agda implementation of what? Well, what their challenge was to implement something called Tarjan's strongly connected component algorithm. So we should probably begin by looking at what that is, and then at what the challenge is. So the algorithm is for finding strongly connected components. So what are strongly connected components? Well, this animation is showing you both the algorithm, and once the algorithm will finish, we'll see the output. This now is the output, and we only saw it for like 1 second, so it will be difficult. So instead, let me move here and add the diagram in front of my face so I can point at it and explain, right? So, what is a graph, right? There are nodes and edges between them, and like those two nodes, they point to each other. They're a component. Those three nodes, they point at each other. Well, this node doesn't point directly to this one, but it points to it indirectly because it points to that node, which points to that node. Whereas, well, also like this one points at itself. All the nodes are indirectly pointing at themselves. So this one is also a strongly connected component. They point at each other. But let's see if I can find a counter example for the thing I want to talk about. Like this one points to this one, which points to this one, but those three nodes are not part of the same connected component because there's not a path back from this one to the first one, or even this one. So it's only when all of the nodes are pointing to each other that they are part of the same strongly connected component. All right, so that's the goal. And how does Tarjan's algorithm compute them? Well, I don't really know, because one big part of the challenge was to make sure that we were implementing the real Tarjan algorithm and not some less efficient version of it. And I was quite concerned that in translating the algorithm from, it was originally in Java, the sample implementation they gave, to Haskell or Agda, that I might be losing some of the performance characteristics, say by converting from an array to a linked list. And so, as you will see, I decided to keep the code as close to the Java implementation as possible. So we are using arrays and mutable variables. It doesn't look like the usual pure code that I like to write, but that was not the point. The point was not to write elegant code, but to prove something about the imperative code. All right, so, well, perhaps it would be useful to try and figure out together how the Tarjan algorithm works. So let me see if I can add the other frames of the animation. First frame, that's the result, that's all of the strongly connected components. This is what we want to get to. And we do so by doing a depth first search. We start from one node, we explore its neighbors, and then its neighbors, and then its only neighbor is a node we've already visited. And something happens, because presumably, well, we know that since we're in a depth first search, that all of the nodes we have visited so far are pointing at each other, and so when we come back to the previous node, they're all part of a strongly connected component, because we can go through the path we just went through for the depth first search and through the node that goes back up. So all of those nodes are all connected to each other, so they should all be part of the same strongly connected component. So I guess that's what happened next. We go backwards for some reason until we reach the point in the depth first search where we're pointing back and we're adding them all to a strongly connected component. That makes sense. And then what do we do next? Well, in a depth first search, which starts at a given node, would be done. We've visited all of the nodes that are reachable from it. But here, I think what we're doing is that we're just picking some node we haven't visited yet and starting there. So what do we do next? We visit its neighbors, and now we have a choice, like we could visit above or back to node 4, I guess. So those numbers have to do with some of the data that we'll be keeping track as part of the algorithm, which we're both trying to understand together, even though I've already implemented it a bit blindly. So will the algorithm go up or left? It chose to go up, and well, that's not a strongly connected component, so what will it do next? It has to go either left or right. It chose to go right, and then it has no choice. It has to go left. Oh, go left. Yeah, so by going left, again, something happens. It has to go backwards through the list of nodes that it was evaluating as it was doing the depth first search until it finds the node we're pointing to, and those are all part of the same strongly connected component, right? Excellent. So now we can't do as we were doing before and just pick a new node to start over from, because, well, we're not done with the current node, right? We started with 4. Oh, I've been pointing at the OBS screen the entire time instead of pointing here, haven't I? So you haven't been seeing my mouse. Okay, but hopefully the words were enough, right? So yeah, so we started with 4, and we are not done. Like in the process of exploring 4, we found a strongly connected component, but for example, we haven't followed this arrow, and like maybe 5 had more arrows elsewhere, and in fact 6, we haven't yet explored this arrow, so the depth first search is not done. But all of the nodes that were part of the strongly connected component, I think they're all done. And so as we were backtracking, I guess we were done with 7, we backtracked, and well, are we done with 6? There's still this arrow. I'm curious what happens with it. Let's see what happens next. Apparently we are done with 6. We're not following that arrow. We're going back to 5 and exploring its other arrow, its that arrow. And so, oh, that's another strongly connected component. So we backtrack, we mark it, we start from a new node, and that node is its own strongly connected component, and we're done. Okay, so I think we have an intuitive understanding for Tarjan's algorithm now. We like go around, find cycles, backtrack, and then mark it as part of a new strongly connected component. I would just like to understand the numbers. Let's go back to the beginning and make sure we understand the numbers, because we'll be manipulating those numbers throughout the algorithm, throughout our implementation of the algorithm. So we begin with the node 1, and there's this other number 1, which I think is something like the lowest number to which it points. So 2, node 2, node 3, and yeah, now we know that node 3 is pointing to a node that has been visited before. It has a lower number, 1. So that's how we know that something happens, I guess. As we go back, we update. We know that they are all part of the strongly connected component identified by node 1, I assume. Cool. And then 4, 5, 6, 7. So I'm predicting that since 7 is pointing at 6, that it will see that 6 is smaller than 7. It will update the second 7 to be 6. It will say 7, 6, and then it will go back and update. Well, 6 is already pointed at 6, so they will both be part of the connected component called 6. Yeah, okay, and then back with 5, I predict it will say 5, 4. And finally, 8 stays the same. Okay, so I think we understand at least a little bit the numbers. I might be wrong about the if the number is smaller, because it might just be if it's a node that is marked as visited or something. But we have some intuition to anchor our thoughts on as we go through the code. So Pion or Rek gave a little bit later or earlier, not sure where, a link to this Java implementation of the algorithm, and pointed in particular to this line that they wanted to make sure that when this line is ran, we don't do any runtime check in order to make sure that it is safe to call pop. So there's a stack involved in the algorithm, and apparently at this time of the algorithm, we know that the stack is non-empty, and so they don't want to waste time doing a runtime check. They don't want the computer to waste their time doing a runtime check. Is that what they say? Implement the algorithm in such a way that you never need to use a runtime test to check something that is known in advance. So there's many other things, other places in the algorithm where we might need to use a runtime test, like for example, to check if, like I said, we'll be using arrays. Like if we want to use an array in a memory safe way, we probably want to check whether we're indexing inside or outside of the bounds of an array whenever we read or write into an array. But if we know that, like in advance, statically, that the index is within the bounds, then we don't need to do the check. And so I cheated a little bit because, well, if, like, you don't need for it to be statically known for it that it is safe in order to not do the check. Like, if you know, because you've analyzed the algorithm or something, that it will be inside of the bounds, then if you don't do the check, it will still work because it will be inside of the bounds. And if you're wrong about that, like it will seg fault or something. So since they were particularly concerned about this line, like I did like all of the heavy work to make sure that statically, yeah, for sure the stack is non-empty at this point, but like all of the other places where I'm accessing an entry inside of an array, I didn't bother to statically check that indeed the index is smaller. Like I could to just make the code needlessly longer, and I wanted to focus on that thing that was the thing that was considered the hardest part of the challenge. Because like checking in Agda that a number is within an array is like relatively easy. Like I just need to use a fin instead of a nat. Because fin is indexed by a number, like fin tree has 3 inhabitants at 0, 1, and 2. And so if the array has length 3 and we use a fin as index, we know that it will always be within the bounds. But except I didn't bother doing that. I didn't even use a nat actually. I used an int because again, I'm trying to use the imperative algorithm and they use ints. Okay, so I think we should now go to the Agda code, and I have here on GitHub the code that we'll be looking at here. And so let me paste that link. Like it's at the top here, but just so you don't have to type it, I will paste it in the chat and in the YouTube description, if I remember. Looks like it overlaps a little bit. Let me move it down, not this one, this one. Move it down. Here we go. I'm sure it will get overlapped by other code later on, but at least when I'm in the at line 0, it will overlap. Okay, so here is what Agda code looks like. Just like in Haskell, it tends to begin with a very long long list of imports. I will explain all of the things that I am importing soon. First thing that might be surprising if you're used to Haskell rather than Agda is that it's open import instead of import. That's simply because of a Python-esque thing. Like, you know how in Python you can import the module and then you can use like the name of the module dot the thing that you've imported. So that's what happens by default if you import. And if you open import, then like instead of using module.foo, if you want to access the definition named foo inside of the module you have imported, you can now use foo. And using is just like the qualified import in Haskell. I'm only bringing those values in scope directly. And if I want to use anything else, I would need to use the name of the module dot the name of the thing. If that's even possible. All right, so that's a relatively long file. Yeah. So maybe I should not explain every line throughout the lines. But what I want to show is that there is a very close mapping between the code in Java and the code in Agda. So I would like to see them both side by side. So like this maybe? Can't make the window smaller than that, apparently. Okay. So this main function is creating an example graph which is the same as the example graph we've been looking at in the animated GIF. I'll make it appear again. Okay, so it's this graph. And at the end, we want nodes 1, 2, and 3 to be part of the zeroed connected component. So that's why we want the output for nodes 0, 1, and 2 to be 0. And then nodes 3 and 4. 1, 2, 3. Yeah, nodes 4 and 5. Here, those two are in the second, so 0, 1, 2, triangle connected component, and then after that 6 and 7 are in the first, 0 first, and finally the last line, the last node, the 8, is in its own strongly connected component. Okay, so that's what we want, and indeed when I run my program, it gives the expected output. And yes, I'm running my Agda program. This, perhaps surprisingly, is unusual for Agda programmers. We tend to only type check them, and that's because typically we write in Agda like some proof level stuff, and we're only interested like in knowing that the proof is correct. We don't really need to run it because there's nothing to run. And in fact, large chunks of the program are being executed. I should remove that from my face. There you go. A bunch of parts of the program are being executed as part of the type checking because with the dependent types, it's quite common to evaluate code as part of type checking. So while we don't run our programs, like the big parts of it run anyway, but still it's unusual to compile it and then run it instead of running it as part of the compilation process. But the reason I did it now is because, like I said, I want to use like real arrays, and so I'm shelling out to Haskell. Is shelling the correct verb? I'm not sure. I'm using the FFI, the Haskell FFI. Right, well, Agda's FFI allows me to call Haskell from Agda. In Haskell, you might be used to using the FFI to call C from Haskell, so that's not what I'm doing. Although, like, since it is using arrays, like, presumably it's doing something with raw byte buffers. Maybe natively, maybe via C. I don't know how arrays are implemented. Probably natively. Anyway, so that's why I'm running it, because I need to run the generated Haskell program. So I'm compiling Agda. In the process, it is generating some Haskell code. It is then compiling the Haskell code, and what I am running, this source/main executable, which is right next to my source/main.agda file that I currently have open. This is the result of compiling the Haskell program. Okay, and we can even look at the Haskell program if you want. It's in, where is it? Malonzo. I think it's the name of their main.hs. Yeah, so this is the generated code. Like, this is Haskell. Like, you can tell that this is Haskell because we're using 2 colons for separating the names and the types, whereas in Agda they use 1 colon. And there should be a main somewhere in here. That looks... I would have expected something that looks a bit more like that main example graph, Tarjan, so on. But like, there's 1, 2, 3, 4. There's 4 lines, and they have oh, wait. D446, that's the type. Okay. No, that's not the type. Like for some reason I thought it was saying like colon, but no, it says main equals COE, whatever that is, of D666. So this is main, and okay, this is the type. It's IO of unit, so that corresponds to what I have here, IO of unit. So I would expect the first thing to be calling make example graph. So is D26 make example graph? Where is D26 defined? It's not defined in this file. Oh, in monad classes. Oh, because of course, this is do notation. So the very first thing that happened is not that make example graph is called on a bunch of arguments, but rather that bind is applied to make example graph and the continuation. So what we should be expecting is that the first argument of D26, which is apparently the compiled name for bind, is applied to D2. Simple IO, it's not in this module either, so that's probably like the dictionary proving that IO is a monad, and then some erased argument. I will talk in depth about erased arguments in a moment. And what did the next have? Array. I would expect at some point to have something from this file. And well, almost most everything, like the 6 is prefixed with array and so on. But this D42 finally is something from this file because it doesn't have a package prefix. And I am guessing that D42 correspond to make example graph. Let's go and see that. D42 main.n, not at all. Okay, maybe I shouldn't be messing around with the compiled code and just trust that it matches the code I wrote here. Can I search for make example? Oh, the make example graph is not from this file actually. So so maybe I should be looking for the call to Tarjan, which should be near. So Tarjan is name 142, D142, which should occur. Yeah, it occurs still in main. Pretty close, right? There was the first thing which happens, and the second thing which happens, and then the next thing is D142. Okay. So there's some semblance of correspondence between the Agda code and the Haskell code. Let's focus on the Agda code because it's more readable. Okay, so I'm creating a graph. I'm calling the Tarjan algorithm on it, and it produces an int array indicating which component each of the node belongs. And this Tarjan algorithm here, I claim, corresponds to the Java algorithm. So let's make it visible again. Where is their main? Their main here does something similar to what I'm doing. It is initializing a graph. Not sure from what. And then it's calling Tarjan, this thing. I'm not sure what happens when I select it. I would have expected a link or something. But Tarjan parenthesis. Yeah, so this is the constructor, and I'm not sure why they do it from the constructor. Must be a Java idiom. But inside of the constructor, they receive the graph, just like my Tarjan does. I'm a bit confused because here... Okay, yes, this is an Agda idiom I can show you. So Tarjan here is receiving a graph as input and producing like an IO action that produces the output array. And here it looks like, okay, well, that's weird. Tarjan doesn't seem to be taking in the graph as input, but it does return the IO array of int. So where is this input gone? Well, you might notice that Tarjan is indented a little bit to the right. And so what's happening is that all the way up here, higher than that, higher still, more. Okay, here we have an anonymous module. So in Haskell, right, you need to have the module at the top and then all of your definitions. In Agda, well, you tend to have a module at the top, like I do here, module main, and then the definition. But I can have another smaller module inside of my module, and like I can have a bunch of nested modules in there. Well, that works with the import system I've mentioned before, right? If I define a module named foo, then like inside of this same file, but outside of that like sub module, I can refer to the things that are defined inside of the module foo with like foo dot the name. Unless I open it and an anonymous module named underscore automatically opens the module so that I can refer to n as n and not, in this case, well, underscore that n, if it was named foo for that n. However, there's one big difference, which is that inside of this anonymous module, n as type int, but outside of the module, if I use int, it will have type graph arrow int. So all of the definitions inside of the nest module are prefixed with all of the arguments that are given to the module. So I use that extensively in order to simplify the various type signatures by kind of introducing a lexically local definition. So this G is local to all of those definitions, and so like, within that module, we all know what G means. It's all the same G, but outside we need to specify what the G is. So that's because all of the parts of the Tarjan algorithm, they're all talking about the same graph. I just didn't want to have to pass it around. So that's like an alternative to something like the reader monad that we'd use in Haskell in order to avoid having to pass around the argument. This is a module-based solution instead of a monadic solution. Anyway, so Tarzan has now access to G. It's a graph, and let's see what it's doing. It's initializing a bunch of arrays, and then it's calling Tarjan 4. So what's happening here is that, same thing, right? I'm in the Java side, I'm initializing an array of booleans. Here, same thing. I'm initializing an array of booleans, initially of value false, naming it marked. And then I initialize the stack. I don't see that I do it. Oh yeah, I do it here with stack. Shows the stack, slightly different ordering. But otherwise, like it matches like pretty much one-to-one. I initialize a bunch of arrays, and then I begin a for loop. And I didn't put the for loop in line here. I'm using the more functional idiom of recursion. So I'm calling the function Tarjan4 that represents the rest of the function from this point on, and that function will like call itself if it wants to loop back to the beginning of the for. So that will be the overall idea of how I'm translating the Java to Agda. So now let's go to, well, I said that I wouldn't do it line by line, but like whenever there's a line that introduces a new concept, I should probably go over it. So here I'm using lift, and I'm using new array, and I'm using with stack, but let's talk about that later. So lift is lifting what is it lifting? Because there's two different complications in there. There's some kind of index monad, and there's also that I want to lift some IO from Haskell into the Agda IO. So I'm not quite sure which of the two this is. Yes, I remember now. It's lifting some regular Agda IO into the indexed IO monad that I will explain in a moment. But first, let's look at the regular I/O. Let's look at new array. Because here, this code here, main is running in I/O, and so is Tarjan, but with stack is introducing this index I/O. So that's why, I'm not calling new array here, but like if I had to call new array in main, I wouldn't need the lift, but inside of Tarjan, I do. So let's go see the definition of new array. This is something I wrote. Because again, like in Agda, we are like more natively, we would use linked lists or vectors or something, which are still linked lists, but in Agda, the word vector means a linked list that is indexed by its length. Whereas here, I really want to use arrays, like contiguous block of bytes. And I do that, or at least a contiguous block of pointers. And I do that using, like I said, the FFI to call out to Haskell functions. So Haskell does support some arrays, and so here's what this is doing, right? So I'm using the postulate keyword in Agda to define the type of the various constructs that I want to import from Haskell. And then in this pragma comment, I say what I want these things to correspond to. So like I do some Haskell import from data.x and ghc.io array. Those are the modules that happen to be providing everything that I need in those definitions below. And then for each of the things I gave type 4, I need to give a definition in Haskell. So the Agda type array, which is a type constructor, corresponds to the type constructor IO array int in Haskell. So since it's a type constructor, right, there's a type missing. So if it's an array of int, then this would correspond to an IO array int of int. So the first type parameter is which type we are using to index into the array. I'm just using ints. Normal. Haskell supports wilder things, but we're sticking to the normal imperative style of just indexing into an array using an int. And then not written is the extra argument, but like I could have written an array of A is an IO array int of A, presumably. Okay, so new array, I'm delegating to new array, need to specify the lower bound and the upper bound, so I decide that I want them to be 0 indexed. We can find the size of an array, like the number of elements. And I'm using this cute syntax to read the value from an array and assign the value to an array. Like I could have just called this read array and write array, right? This would have worked too. But in Agda, Agda supports some very fancy infix. No, it's not. Multifix, I think, is the official word for defining operators that consist of multiple parts, and the arguments are between the parts. So, like to read at a particular index from an array, we need to know what is the array and what is the index. And in Java, we would write the name of the array, let's say A, and square bracket, and then the index I, close the square bracket. And that is exactly the syntax I'm using in Agda as well. We can use, so in Java it would be A square bracket I, and in Agda it's a space, square bracket, space, I, space, close square bracket. And the magic here is that this syntax, since Agda knows that this operator is in scope, it magically expands this to underscore square bracket underscore square bracket, so that operator applied to A applied to I. Just some magic, parsing magic, that every position where there's an underscore, we can put an argument there. So That means that this is an operation that takes two arguments, namely the array and the index. All right, so yeah, I do the same thing for mutation. There's a Unicode operator, colon equals. No, just colon equals, that I'm using just to emulate the Java syntax, a square bracket space equals the new value. I can't use equals as the part of a name, but I can use colon equals. Well, I cannot use colon equals, but I can use the special Unicode glyphs that includes both the colon and the equals. That's also a very common Agda practice, to abuse Unicode as hard as we can in order to make the code look nice, but not necessarily be easy to understand how the hell it parses. Okay, so, but it all expands out to just a function applied to a bunch of arguments, and the function has this funky name, underscore, square bracket, colon equals underscore. And it's just implemented by dedicating to unsafe right IO array. I should explain what those arguments that I'm ignoring here are, right? So those are Haskell lambda expressions. So it's that, so you know how in Haskell the type of unsafe read IO array is for all a, it's automatically converts the word for all into Unicode, but you know what I mean. On the Haskell side, if I get an IO array indexed by I containing 8 elements and an I, then I have an IO action that gives me an A, the A that is at that position, or fails with an exception, or even a segmentation fault, because it's the unsafe variant, if I'm reading outside of the bounds. So there is this type level argument A here that is definitely erased at runtime in Haskell, but in Agda it's quite different. So I would write the same type as unsafe read IO array single colon, because we're in Agda. There is a for all keyword in Agda, but it means something slightly differently. So here the A is the name of the argument and its kind is star. Oh, actually it does mean the same thing. Yeah. So for all A, okay. And the reason I was confused is because there's this, it expands out to this longer version like that, where the type is inferred. We infer that it is the type, the kind type. Anyway, A of type, IO array, IA, IOA, so it's almost the same, but notice that it's an arrow here, not a dot, because this is an ordinary argument, and in fact, like all the arguments can be named. Like I can name this array, I forgot an arrow here, and I can name this, well, it's already named. No, I is not the name of the argument. I is the type, right? So I can name it like index of type I. It's probably going to be int. Like I is probably going to be int. It's pretty clear if I write it like that. Okay. So the reason why those names can appear in the signature is because just like this A that we already are used in Haskell to give names to our types at the type level that we're doing a universal quantification over. The types can appear on the right of the dot in Haskell, and same in Agda. See, the A appears here on the right of this arrow. But like I could use also like array or index on the right of this arrow. Like I could say like, if the index is greater than 0, then I'm producing IO of A, and otherwise I don't know, producing an int, or like I could do crazy things at the type level. I can, like I said, write expressions that evaluate at compile time while type checking. Like this is an if I have a concrete index, I can at compile time check if it's greater than 0. and evaluate this if expression down to something smaller, like the result of one of the two branches. And so, so that means that those variables cannot necessarily be erased. The fact that it appears at the type level is not what means that it can be erased, but it just so happens that regular arguments are not so different from the type level arguments. Regular arguments, like array of type IORA, are not that different from type parameters, such as A of type, in that they are both regular arguments to the function. And so that's why here in the type, it is almost the same as what I just erased. I shouldn't have erased it. And I should undo the if. Okay, so now that's a more reasonable version of the type. And also let's call it underscore blah, blah. And why not? Let's use a for all syntax, for all A. Okay. And I guess we don't need the names for the others. Okay, so now that looks a lot like, as a convention in Agda, contrary to in Haskell, where all of our type parameters are lowercase, types by convention in Agda are uppercase, but it's not like in Haskell an enforced convention. So even though it's a type variable, it's still written uppercase. Okay, so now it looks the same, but here this first argument is a real argument, just like all the other arguments, whereas here I've took explicit care to tell Agda that I want this particular argument to be erased at runtime, whereas in Haskell all type parameters are erased at runtime. So that's what this notation is doing, and that's why it means that here I have an argument, the erased argument, that I will need to ignore at runtime. So wait a minute, how come I'm receiving an argument at runtime? Didn't we just said it was erased? Well, when I hope I didn't change anything to the file, otherwise it wouldn't compile anymore. When we were looking at the generated code, there were a bunch of those arguments which just says erased, so that's just like unit or something, or maybe we're probably undefined because it needs to have any type. It's an argument that it still exists at runtime in the sense that we're receiving something, but it doesn't have a value. We can't pattern match on it and do anything with it. And so that's why I had to ignore it with the /_. All right, so already an hour in, I think that I probably won't be able to cover all of the code today, and I should probably stop at what will be a good point. We'll find a good point soon, and I will start the stream, and I will continue explaining the code next week. But for now, today I have explained how to import, how to use Vivify to run some Haskell code in Agda. The rest of this file is not particularly interesting, just some debugging code to print an array. And that's it for this file. Oh, and unit in Agda is called top. It looks like data top is the name of the file, of the type. It's a type, we need to specify the kind whenever we define something. And like in Agda, it's like unit parenthesis for the type, and also unit parenthesis for the value. But since in Agda, types and values live in the same namespace, we can't use this punning, we have to use different names. And so in Agda, it's called TT of type top. And that's why, I guess I didn't write it explicitly because print of XS is already returning unit, but I could be writing like pure of TT here. Wait, no, this is Haskell code. I can't return pure of TT. I would need to return pure of unit in Haskell. But like here, this is returning a top, and in main Yeah, here I'm returning TT. I'm just returning unit, the value of type. Top. Okay, so after all of this time, I went through one line, and not even, right? I went through new array, which is the function we just looked at, right? New array, this one, I'm delegating to new IO array that is taking the bounds and one value to use for all of the elements of the array, so they will all be false, and there was some type inference going on here where I gave it a value of type false, and just like in Haskell, like it figures out that A is bool, nothing special here, but I still have to explain the lift, and I think I will do that next time. So thank you for attending my stream. I hope you enjoyed learning about Agda. See you next time for more Agda. Ciao!